having a artificial creating a artificial brain-like structures that can learn and recognize patterns in data, like much like how we humans learn to recognize faces and understand speech. In the same way, these neural networks understand the patterns in the data. So if you observe this image, this human image, human brain, so this illustrates how a neural network inside a human profile is. So we are actually trying to recreate human-like capabilities in machines. So how our human brain is connected with neurons and all. In the similar way, we are going to connect different neurons and we are giving them our human brain-like capabilities to the machine. And let's understand about neural network architecture. Here, every neural network has three main components. If you say this input layer, hidden layers, and output layers. So this input layer is nothing but our raw data. So we have a data set, right? So it contains some columns and some predicted outcome, right? So this is our input layer, and these are our hidden layers. This is the second one and the third one, which is in gray color. These are our hidden layers. So here in this diagram, we have multiple hidden layers, hidden layer 1 and hidden layer 2. Here, each one extracting more complex features from the data. So these two can extract features from this input data. And finally, we have output layer. So this is where we get our final predictions. So either we are predicting the classification problem or regression problem. Here, what we get the output from. Okay. And these connections. So here we have these lines, right? So this input layer X1 is connected to, if you observe this, it is connected to all of the hidden layers, and X2 is also connected to all hidden layers, and similarly X3 and X4. And again, this hidden layer 1 is connected with all of the other hidden layers, and again, all of the neurons is connected to other neurons. So these connections represent weights, which determines the strength of connection between neurons. So these patterns help us to analyze different patterns in the data. These lines. Okay. Now let's understand about okay, what is ANN, what is artificial neural networks, everything in detail. So if you observe this diagram, so this is the simple neural networks. So this is a simple neural network with the three different layers like input layer, hidden layer, and output layer. So input layer means a raw data. So hidden layer means the layer which can able to recognize the patterns, and the output layer which gives us the output. Here, our input layer basically has two features here. Let's take an example. So we have two features here, weight and height. And in hidden layer, it contains two neurons, H1 and H2. And in output layer, we have O1. This is our output layer. So for example, we have weight and height, and we are going to predict the gender based on weight and height. And next. So this is how generally simple neural network looks like. And in this neural network, we need to understand the term forward propagation. Okay. So forward propagation means how the data flows in this neural network. That means first we have the input layers, and this input layers is sent into the hidden layers. And again, there are some calculations happening in this hidden layer. And then finally we'll get the output. So this entire process is forward propagation. And this neuron, some calculations will happen. So let's discuss what are all of the calculations, and then what's how the output is generating or not. And next, after we are getting this output, then we are going to calculate the loss. Let's say like our output is 1, but we got our output as 0 0.8. So then we are going to calculate the loss here. So loss means what the difference between the actual value and predicted value. So actual value value minus predicted value whole square. That is our loss. Okay, after calculating the loss, we are going to do the backward propagation. That means initially here different weights are assigned. So here weights are some values. So some smaller values or larger values. Okay, so these weights need to be updated every time. And for every neuron, if you observe, there is some bias added over here. Okay. So here in every neuron, these inputs are multiplied with these weights. So weights are some smaller values, and this inputs get multiplied in this hidden layer. And what we got the product, it will be summed. So here we have two input layers, and it's connected to two neurons in our hidden layer. Okay, all these will be multiplied. So weight into W1, weight into W2, and again height into the height into W1, height into W2. All these will be produced and summed. And finally, to this some bias will be added. After bias, some activation function will be applied. Okay, don't worry, like this activation function, this bias, I'll explain one by one carefully. So first I'm trying to explain how does the enter process work. First, we have the input layer. So this input is sent into the hidden layers, and after some processing in the hidden layers, we'll get the output. And then we'll calculate the loss function based on the loss function. So our main aim here is to decrease the loss function so that our model accuracy will increases. So we'll calculate the loss function, and then we'll do backward propagation. Backward propagation in the sense, so initially we have some weights and biases. We will update these values. So we'll update these weights and biases values so that again it will compute from the start with the different weights and different bias, and again we'll get some output. Then again we'll check the loss function. Again, if there is more loss, then again we'll repeat the same process. Forward propagation, calculating the loss, and then backward propagation. So this is what everything happens in this entire neural network. So now let's understand each step very carefully. So 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 if you look at this left side diagram, this white color one. So here there are some different mathematical calculations, right? Here, let's take an example. We have two different neurons over here, A naught and A1. So A naught represents neuron in the current layer, and A1 also represents one of the neuron. Okay, and these neurons are connected to here A naught, A1, A2, and A3. So these are our hidden layers. Once again, this A naught, A1, A2, and A3 are hidden layers. And again, this neuron is connected to this A naught is connected to all of these four other neurons with some weights. See these red color lines. So this entire first one is connected to four of the neurons with the W0, W00, W10, and W20, W30 are the respective weights. Now, observe this equation. Let's say, like, take this example. A1 equals to sigma of W10 A naught plus W11 A1 plus B1. Here, what this equation is, let's say, okay, now we have the A1 function, right? A1. And this alpha is our activation function. Okay. So generally, I'll explain more detail about activation function, but actually what does this activation function do means, especially in a neural network, this is a mathematical function which determines the output of a neuron based on its input. Okay. So here, then we'll observe the formula over here. So this A1 equals to first. So this is our A1, right? So this second neuron A1. So here, if you observe this, let's take a simple calculation. Let's understand a simple one. Here, what does in every neuron, what does the total process happen means, this weight is multiplied with this input. Let's take for example W10 as our weight. So this W10 is multiplied with A0 plus again like W1 over here. So to this A1, so this is our neuron rate A1. So we are getting two different weights for A1. So we are getting W10 and also we are getting W11. So we are getting two weights over here. So the first weight W10 is multiplied with this neuron A0. So this is our input neuron A0. A0 into W10 plus again A1 into W11. W11 into A1. Okay, this weights is multiplied with this input feature, and then finally we are adding the bias term. bias term. So again, if
Yeah,
you're second one,
sorry, sorry, I have one question here. So example, A0 is equal to sigma W00 A0 plus W01 A1 and plus B0. Okay. So
okay.
why not that equation can be A0 is equal to sigma um, Y01 sorry W01 A0 plus uh, W21 A1 plus B0. Why not that equation? I'm just
Why in
switching
the sense
actually.
like,
Yeah, I'm just trying
okay,
to
okay.
switch actually. So if we switch the numbers, right? If we switch the W weights, right? Then what happens basically?
It depends actually. So here, I assigned so if you observe here, so this is some random weight over here. So this, if you consider this A naught, so
Mm,
this neuron is actually connected to all of these four neurons, right? With
yeah,
different weights. Okay. Now
right.
let's say like I'm calculating for this one, first one, this A naught of one. If I calculating for this first one, so I need to check what are the weights I'm getting. Okay, I'm getting weight from this A naught with the weight as W00, and also I'm getting one of the weight from A1, that is W01. Okay, so this W00 will be multiplied with A naught of 0 plus this W01 is multiplied with A1 of 0. Okay, and finally a bias term will be added. Let's say like for this first one, A naught of 1, the bias term is B naught. Okay, for second one, it may be B1, and other will be B2 and B3. For every neuron, there will be a bias term also.
Okay. So that's why I'm just a confusion. So why not
Okay.
we can why not we can switch the expressions basically?
We
Yeah,
can, we can. So if you see in the backward propagation,
Uh-huh.
every time these weights assigned will be changed over here. So when the weights are changed, again the calculation will change. Again the terms will change.
Okay. Yeah. Okay. That's fine.
Okay, now let's understand this about this neural network concept with a simple example. So let's say like we have two inputs, x1 equals to 2, x2 equals to 3, and we have some initial weights as w1 equals to 0.5, w2 equals to 0.3. See over here, so x1, so this is our first input 2, and x2, this is our second input 3, and we have one hidden layer over here, and then the weights are w1, w2. W1 is zero point 0.5 and w2 is 0.3. These are initial weights, and there is also a bias term added to this neuron, which is zero point 0.5. And also, there is another one more parameter called learning rate. So I'll talk about this learning rate later. So the value of this learning rate is 0.1. It is some random number. So 0.1. Here, our target is 1 over here. So we are going to predict the target. We are aiming for the target output of 1. Okay. So our target is 1. And now let's understand this calculation. So how does this network learn, and how does this everything works over here? First, in every neuron, so if you observe this neuron, so first the weights is, as I told before, this weights is multiplied with the inputs. Okay, see this z equals to x1 w1 plus x2 w2 plus p. If you observe this, so for this neuron, we are getting two different inputs with two different weights. So x1 into w1 plus x2 into w2 plus bias term b will be added. So observe this calculation. So x1 is 2, 2 into the weight is 0.5 plus the second input is 3 and the weight is 0.3 and the bias term. So let's say like our bias is 0.5. So 0.5 is added over here. So 2.4. And on top of this calculation, an activation function will be applied. Okay, this activation function help us to determine the output from our neuron. Okay, let's say like we have an activation function called sigmoid. Okay, I'll explain what is the sigmoid and what are the other activation functions. For now, let's say like it's a sigmoid activation function. The formula for sigmoid activation function is 1 by 1 plus e power minus z. So 1 by 1 plus e power, our z value is 2.4. So if I calculate this, I'll get the output as 0.92. Okay. So we are aiming for the target of 1, but we got the output of 0.92. So now our output is predicted, and then we are going to calculate the loss function. Here the loss is 0.08. So we need to get the target of 1, but we got 0.92. So the error over here is 1 minus 0.92 is 0.08. So this is our error. So this says we need to increase our output by 0.08. Okay. And next, we are going to do the back propagation now. Okay. In back propagation, we generally will change these weights. We will calculate the different weights based on the error function and the old weights, and we will initialize different weights for this in the back during the backward propagation. And then the neural networks learn the learn again with the new weights and new bias, and then again the output will be generated. So this is an iterative process until the error gets decreased. Okay. So during the backward propagation, we need to update the weights, right? So these weights will be updated using this formula. So let's say like our initial weights are W1 equals to 0.5, W2 equals to 0.3. So here our goal is to update this weight so that the calculation again the neural networks learn with the different weights, and again we'll get different output. So in order to update this weight, we are going to use this formula. So W new, that means new weight equals to old weight, W old minus alpha. This will be our running parameter into derivative of j by derivative of w. So this is derivative with respect to loss by derivative with respect to weight. So this is our gradient. That means, so we are going to individually calculate this weight function. So if let's say like let's take this derivative. Okay, consider it is like derivative of e by derivative of w1. Let's say like we are going to update this weight w1. Okay, we need to update this weight w1. So here it follows a chain rule of derivative. So maybe in our 10th standard or intermediate, so we'll learn about chain rules and all. So in order to calculate this derivative, to update this weight w1, we are going to follow a chain rule over here. So first, our output is y. Okay. First, we need to write this as derivative of loss with respect to derivative of y, and into, and again this y will be dependent on this z term, this one, this neuron. Okay. If you observe this entire structure, this y is dependent on this z, and this z is dependent on this w. So we need to go in this process. First, derivative of e by derivative of y into derivative of y with respect to derivative of z, this one, and then again derivative of z with respect to derivative of w1. So we need to update this weight w1. If you want to update w2, then again derivative of loss with respect to derivative of y into, again derivative of y is with respect to z into derivative of z with respect to this weight w2. Okay. So whichever weight you want to update, you need to go in a backward way. Okay. So this is a chain rule. Okay. And then after computing these derivatives, so we are getting the values like minus 0.118 over here. So our weight updation formula over here is W old minus learning rate into derivative of loss with respect to the gradient. That means with respect to the weight. So W old. So what is our initial weight? 0.5. So 0.5 is our initial weight minus learning rate. Here learning rate help us to increase the weight updation process. So our main goal over here is we need to decrease the weight, right? So that let's say like um, our weight over here is 0.08 over here, right? Next, we need to decrease the weight to 0.06 or 0.05 or 0.04, right? So this learning rate help us to boost this entire process by decreasing this error. Okay, that's why we are, so scientists have introduced this learning rate. So let's say this is 0.1 into, so our derivative calculation is minus 0.0118. So I'll get my new weight over here is 0.50118. Okay. So this zero point 0.5 weight now updated as 0.50118. Okay. And again, we'll calculate for W2 also in the same way. Okay. After calculating W1 and W2, our model starts training once again. Again, our inputs are will be multiplied with this weight, and again the bias will be added, and we'll get the new output. Okay, then again it will check the loss function, what is the error. So if there is error, then again backward we will do the backward propagation, and again it's an iteration process. So here in
Okay,
every neuron,
one more question, sorry.
yeah,
Learning rate is always 0.1, or is it constant kind of thing, or what is it actually?
so it is not a constant term. So generally uh, we'll give this learning rate as 0.1, but you may also give 0.2, 0.3.
How we are calculating
So you
that?
need to basically, yeah, so basically you need to test with the learning rate. So with some higher learning rate, you may get the higher error. So our aim is to get the lower error, right?
Right, right.
So we need to try with some different values, zero point 0.1, zero point 0.2, zero point 0.3. But
And
generally, some zero point 0.1 is a default rate.
okay, until we get the target is 1, we have to randomly update the learning rate to reduce the error. That's it, right?
Yeah, so that is like tuning the algorithm more.
Okay.
So generally, with zero point 0.1, we are going to train this neural network. So if you want, for let's say like if you have some larger data sets, then you may go for zero point 0.2 or zero point 0.3.
Until what
That's how
number?
like,
Until what number? Is it 1, or
and
like below 1, or what is it actually? The number.
if you give the value as 1, 2, then probably you may get the very high error. Okay,
Okay.
so generally we'll keep it in points only.
Okay. Points up to zero point 0.9 or something, you mean?
Yeah, maybe zero point 0.2, zero point 0.3 until zero
Okay.
point 0.5 you may try with until zero point 0.5. So that's the best case.
Okay.
So the thing is, a learning rate is kept below like point 0.1, point 0.2 because we don't want to update the weights like frequently. So we don't want to change 3 to 2 and then 2 to 4. So we want to update slowly. That's the main essence behind adding a learning rate.
Okay. Okay. Thank you.
So here we use the Sigmoid activation function, but here there is not only a Sigmoid activation function, so there are different activation functions. So based on our problem statement, we need to go for this activation function. So let's understand what are these activation functions and all. So generally, these activation functions is a mathematical function, so that determines output of a neural network. Okay. So as here, so it determines the output of the neural network, right? Okay. It takes the weighted sum of input plus bias, and it transforms that value into some output value. Okay. So now let's understand what are the different kinds of activation functions we have. So before diving into the activation functions, let's understand about vanishing gradient problem. Okay, what is this vanishing gradient problem? So when training our deep neural networks, so we are using this backward propagation rate to calculate different gradients and updating weights, right? So basically, these derivatives are used to update our weights. So as we move backward through these layers, let's say like if you have a very big neural network, so here we have only two sets of layers. Let's say like if you have 64 hidden layers, like 120 hidden layers. So in the larger deep neural network, during backward propagation, if you want to update the initial weights, so when we are calculating these derivatives, these activation functions give us the smaller values. Okay. So let's say like here our W1 is zero point 0.5 and it is changed to 0.50118. So what if this W1 is zero point 0.5 itself again after backward propagation, or else what if our weight is 0.51? Okay, there won't be, so our older weight and newer weight is almost similar. Okay, if our newer weight and older weight is almost similar, then again you may get the similar calculation. Then it is no use, right? So what we want, we need to decrease these errors so that the weight functions need to be changed. If we are getting the same output again, so there is no use of doing this backward propagation, right? So in very deep neural networks, it will, these derivatives, okay, whatever derivatives you are calculating, this will give the very smaller values. Okay, so let's say like if you subtract that smaller value from this initial weight, you may get again again a value which is close to the initial weight only. Then your weight, then again your weight updation won't happen very much efficiently. And again, if your initial, if your error is 0.08, then you may get the error as 0.07 or 0.75, which is again close to the error, right? So this vanishing gradient problem generally occurs in a very deep neural network. Okay, when we need to update the initial weights, then these derivatives generates the very smaller values. Then our weight updation won't happen much and error won't decrease. Okay, so this is what the gradient vanishing gradient problem means. Okay, so generally we have different activation functions. So sigmoid, tanh, ReLU, and variants of ReLU and softmax. Let's understand this one by one. So first we have sigmoid activation function. So this sigmoid activation function transforms any input value into a output values between 0 and 1. Okay. So it transforms any input value into an output between 0 and 1 only. Okay. So this function, actually, if you use this function, we may face the vanishing gradient problem. So generally, this sigmoid activation function will be useful in the case of binary classification. So in binary classification, we need the output ranges of 0 or 1, right? So let's consider if it is a spam detection problem. So we need to classify our email as spam or not spam. So here we need the output values of zeros and ones only over here. Whether it may be 0, that means it's a not spam, 1 means it's a spam. So if you want our output value in this range, then it is best to use the sigmoid activation function because it has the capability of transforming any input value into output between 0 and 1. So but so if you observe this, this is good for a probability, so it is very good for a binary classification problem when you have the output range of 0 and 1. But again, it suffers with the vanishing gradient problem. So as it gives the values of zeros and ones only, so during the derivatives, so when you are in the during the backward propagation, you will calculate the derivatives, right? So during this derivatives, it will generate the smaller values. And in the case of deep neural networks, our weights won't get updated properly, and our error will be same as the previous one. So this sigmoid activation function suffers with this problem. So for this problem again, the scientists have researched about this activation function, and they came up with another one, tanh, another activation function. So this tanh transforms input value into output from -1 to 1, the range. So sigmoid will transform into 0 to 1. Tanh will transform the values to -1 to 1. So here, this tanh actually, so this tanh function, it produces some greater values, some greater derivative values than sigmoid. So that's why it produces some higher values than sigmoid. Then your weight updation will happen very smoothly. So not that much, but it is better than sigmoid function because the values, the derivative values it generates will be closer to 1. So that will be greater than sigmoid function. Okay, then our weight updation will happen and our error will be decreased. So this tan h is better in the case of weight updation process as these values are -1 to 1 and the derivatives values will be also somewhat bigger than sigmoid function. And if you see about ReLU, the next activation function, again in tan h also still suffers from vanishing gradient problem. Okay, though it gives a bigger values than sigmoid, but still, so during the deep neural networks, so it won't update the weight much properly. It still suffers from this vanishing gradient problem only. Here the sigmoid suffers from the same problem and tan h still suffers from the same problem. So we got the another activation function, ReLU. So it is pretty straightforward. So if you observe this formula, ReLU activation function is max of 0, comma x. The sigmoid one is 1 by 1 plus e power minus z. And your tan h formula is e power z minus e power minus x or z by e power x plus e power minus x. So this is your tan h formula. And your ReLU is pretty straightforward. So max of 0, comma x. Here that means, so it outputs the same input value if it is positive. Let's say your input value is 5 and your output will be 5 once again. So it outputs the same input value if it is a positive value. And if your input is minus, then your output is 0. Okay. Let's say if your input is -2 or -3, you will get the output as 0. If it is a positive input, then you will get the same value. Okay. Max of 0, comma x. So here, this ReLU prevents the vanishing gradient problem. Let's say like your input here is, for example, 4. Then your output is 4, right? So it's a bigger value. So when you calculating the back during the backward propagation also, your derivative values are very big and your weights will get updated efficiently. Okay. But in the case of sigmoid and tan h, your derivative values are very small. But for ReLU, it is somewhat very big than sigmoid and tan h function. Then your vanishing gradient problem will be solved. Here the weights will update properly and your error will be decreased by using this ReLU activation function. But if you go to disadvantages, it suffers from the dead neuron problem. So the main drawback for this ReLU activation function is dead neuron problem. So dead neuron. That means, let's say like your output value is 0. Okay. So during the backward propagation, the derivative also will become 0. Okay. Then the entire function will become 0. So if your new weight is 0, then then the weight updation won't happen. And during the second process, so second iteration also, your weight remains same and again your error remains same. Okay. If your output is 0, that means weight updation is not happening here and your neuron is dead over here. So if the value is 0, then it will face a dead neuron problem. So the neuron becomes 0. It will become inactive if you get a negative input. Okay. So this is one of the disadvantage with the ReLU activation function. Then we have leaky ReLU. So this leaky ReLU slightly modifies the standard ReLU function by keeping a small, so see this, it will keep a small gradient. Okay. Small, typically 0.01 terms of x. That ensures, for example, let's say it's like same like ReLU, but what's the difference over here is if you have the positive input, then the output remains same. Let's say if your input is 2 and then your output will be transformed as 2 only. If your output is negative, then that negative output will be multiplied with 0.01. So initially in ReLU, if your input is negative, then your output is 0. But in leaky ReLU, it will your negative input is multiplied with 0.01. To ensure why this is happening is to ensure our neuron is not dead during the backward propagation. So initially, your neuron is suffering with the dead neuron problem, right? With the ReLU. That's why this leaky ReLU came up with the solution of multiplying 0.01 with your input so that it won't face the dead neuron issue. Okay. So that is the biggest advantage of the leaky ReLU. So it solves the ReLU activation function disadvantages. Okay. And next we have ELU, exponential neural network. So again, this neural network, if you observe this, for again also same for the positive inputs, your output will be the same. So if it is your input is 3 and again your output is 3. But for values which are negative, then it will compute this one alpha of e power x minus 1. Here alpha is some value and e power x. So e power x minus 1, that means x is your input. So it will calculate in this way alpha of e power x minus 1. But what is so what is the most important thing about ELU is it helps our training faster way. Okay. But if you observe this, for calculating the negative inputs, so we are calculating with this formula alpha of e power x minus 1. So generally, wherever you see this e power in your calculation, here also in sigmoid e power minus 6, also in tan h, there is an e computation over here, right? So generally, these computation are very expensive. It takes more time to train your model. Okay. So this is the biggest advantage if you see e power in your formula. So this sigmoid, tan h, and ELU are computationally very expensive. That means computationally it takes more time to train your model. Okay. And we have softmax. So this softmax activation function converts a vector of numbers into a vector of probabilities. So this is somewhat different from this sigmoid, tan h, ReLU, leaky ReLU, ELU. Softmax generally works on the basis of probabilities. Okay, let's say like you have a multi-class classification problem. Let's say your output are cat, dog, and monkey. Okay, so out of these three, you need to predict the one. So whether it is a monkey or whether it's a cat or dog. So finally, after the all the calculation, it will generate some probabilities. Let's say the value of a cat is the probability of cat maybe is 0.2 and the probability of rat maybe is 0.4 and monkey will be 0.5. Okay, so from these three, your monkey is having the highest probability. Okay, then it will calculate these probabilities and based on these probabilities you will get to, okay, which is having highest probability, that may be your final output. So generally this softmax is useful for multi-class classification problems. So whenever you see multi-class problem, then go for softmax. So this is the only activation function. So if you have a binary classification problem, then go for sigmoid activation function. Okay, so that's the best one. Okay, and inside the neurons, okay, so inside the neurons we are applying the activation function, right? So out of all of these activation functions, we need to choose the right activation function based on our problem statement. Okay, so in the modern deep learning techniques, ReLU has become the one of the go-to activation function in hidden layers. So whenever you are you are training a deep learning model. So most probably everyone will try to use this ReLU activation function only. Why? Because sigmoid tan is suffering from vanishing gradient problem. Your weight won't get updated properly. So that's why scientists came up with the ReLU activation function. So this activation function solving this problem, that this vanishing gradient problem. That's why most of the people, like commonly in the in the hidden layers, everyone will use this ReLU activation function. But you may also use sigmoid tan h based on the statement. But this is the common approach. Okay. So during the output layer, so if you have a binary classification function, then use sigmoid activation function in the output layer. The biggest advantage by using sigmoid activation function is it transforms your input features into zeros or ones. So for binary classification, we want those zeros and ones, right? That's why sigmoid is the best choice for the output layer. And again, for a multi-class classification problem, we have no other choice. We need to go for softmax. And for regression problem statement, we are going for the linear activation function. So there is another activation function called linear. It is used in the regression problems. It is again the straightforward approach, just multiplying the input with weights. So the entire process over here in neural networks. So now we discussed about this forward propagation, backward, loss functions, weight updations, right? So first, during initial forward propagation, our input data flows through these neural networks by layer. So each neuron receives input signals and it processes them and sends the output to the next layer. Okay. And again, it's like information passing forward through the network from layer to layer. So this network uses the weights and biases to make a prediction based on the input data. So at this stage, so all the computations, okay, starting from left to right, that means the computation will start from input layers and move to the hidden layers and finally to the output layer. So this entire training process is called forward propagation. Okay, as it is traveling from input to hidden layers, hidden layer to output layer, and then after getting the output, we are calculating the loss calculation. So after this forward propagation, we need to know like how wrong our prediction is. So this loss function measures the difference between our predicted value and the actual target value. Okay. So let's say like our target value is y and our predicted value is y hat. So we are calculating the loss function as y minus y hat. And after calculating the loss, we need to do the backward propagation. So this is where the learning happens during the backward propagation. Here, the deep neural network calculates the derivatives for each weight, and it updates the weight, and again biases by using the chain rule of derivatives. Okay. So the main aim of backward propagation is to update the weights and biases. By with the help of, so there is another term called optimizer. So this entire weight updation happens by using the optimizers itself. Okay. So let's see like what is optimizers, how it is useful. Okay, before going to optimizers, we'll discuss like what are the loss functions we have. Okay, for classification problems. So we have two types, I mean, three types of loss functions: binary cross entropy, categorical cross entropy, and sparse categorical cross entropy. So these three are loss functions for classification problems. So if you have a binary classification problem, then we need to use the loss function called binary cross entropy. So this is a go-to loss function for binary classification problems. So generally, like when we need our network to make yes or no decisions or spam or not spam decisions, okay, then we'll use this function called binary cross entropy. It calculates how far our predictions are from the true values. Okay, y minus y hat. So the closer our prediction is to, so the entire thing over here is to decrease the loss, right? So it will calculate the values between our actual values and the predicted values. Okay. And next we have categorical cross entropy. So if you have multi-class classification problem, then this is the go-to function. Okay. Go-to loss function. If you have binary classification problem, then you need to initialize your loss function as binary cross entropy. And if you have multi-class, then you need to use the categorical cross entropy. Again, same. It measures the difference between your predicted your predicted distribution versus your actual class distribution across multiple categories. Okay, but you have your multiple categories, right? So this categorical cross entropy will measure the difference between your actual and predicted values. And then for regression problem statement, we have loss functions like mean squared error, mean absolute error. So this mean squared error is one of the most common choice for the regression problem statement. So let's say like if you observe this graph, if you observe this red line over here, so it grows more steeply as predictions derive from actual values. That means, so it actually calculates the average of square root differences between your predicted value and actual values, right? So you have your actual value, you have your predicted value. So it calculates the average of, so if you observe this term, mean means average, and square term. So it calculates the average of square root difference between predictions and actual values. Okay, that means y minus y hat by n, mean. So if you do the squaring term, so if let's say like you have a large error, okay. So if you use the squaring term, then there is some possibility for th- becoming this problem to be outliers. Okay, here you are using this loss function, right? So y minus y hat whole square by n. So let's say um, you got your loss as very high value. So if you do the squaring for this loss, okay, then you will get the very high value. So when again during the backward propagation, if you get the larger error, then again it takes more iterations to train your deep learning model, right? So that's why it is more sensitive to outlier problems. Okay, if, when in the case of larger errors, then that's why we have the other another one, mean absolute error. So it is the alternative approach for the regression problems. Again, we may also go for MSE, or we may go for MAE, again on the problem statement. So if you have the more outliers in your problem statement in your data set, then go for MAE, because if you observe the formula for this MAE, it uses the modulus. So y minus y hat whole square, y minus y hat by n, modulus of. So it calculates the average of absolute difference between your predictions and actual values. It won't square your error. So it just calculates the absolute term, absolute difference between your prediction and actual values. So it is very less sensitive to outliers compared to MSC. So making it more robust choice for regression problems. Okay. So these are our loss functions. So for classification, binary or categorical, and for regression, MSC or MAE. So MSC, if you want, if you don't have more number of outliers, then go for MSC. If you have more outliers, then go for MAE. Then we have optimizers. Okay, these optimizers are like algorithms or methods. Use it to adjust our parameters. Okay, so in our during our backward propagation, we need to update our weights and biases, right? So these optimizers actually help us to adjust these weights and biases in your neural network. So why we are updating these weights and biases? Because to minimize the loss function. So the most fundamental optimizer is gradient descent. So this is one of the most fundamental optimizer. So it is just using this formula. Like if you observe this weight updation formula, W n equals to W old minus alpha into derivative of loss with respect to weight. So it uses that formula, that weight updation technique, to minimize your error by adjusting your weights and biases. Okay. And again, here we also have another advanced optimizers. But why we need to go for advanced optimizers means, so the challenge with your gradient descent is, first we need to carefully choose our running rate. So we need to initialize our learning rate as 0.1 or 0.2. We need to carefully choose that learning rate. So this learning rate decides how big steps it takes to decrease our error. So if you initialize your learning rates as a too large, then we may overshoot our target. That means we might go beyond our target. So if you have the if you want the output as 1, if your running rate is bigger, then you may go beyond your target value. Okay. If you initialize your running rate as too small, then it takes more time to get your target value. So the training process will take so large over here. Okay. That's why. Okay. So here the main concept in this with this gradient descent is updating this learning rate. Okay. If you take the larger one, you may go beyond the your target. If you take the too smaller one, then it takes lot of time to decrease your error. Okay, this is one of the biggest disadvantages of the gradient descent, updating this learning rate parameter. That's why we have other parameters, other advanced parameters. So other one is like SGD with momentum, and you have RMSprop, and then you have Adam optimizer. So SGD means stochastic gradient descent. Okay, with momentum. So it is an enhanced version of your traditional gradient descent. So that helps to solve some of the issues your gradient descent is facing. Okay. So it will introduce a new term, beta. Beta means your momentum term. This beta will help us to increase the speed of your deep neural network training process. So you need to decrease your weight rate. So that's why we are multiplying with some other random value beta to increase your speed. So also with the traditional gradient descent problem, you may also faces issues related to noise. That means initially, uh, if you let's say like your error is 0.08, initially it may update to 0.07, and again later it may in the third iteration your error may increase. So from 0.07 to it may go to 0.75, and again it may decrease in the third iteration, and in fourth iteration again it may increase. So your traditional gradient descent which suffers with the noise. Okay, so it will go in the zigzag manner. First it will increase and then decrease and again it increase. So you can't able to identify a specific pattern. Okay, that's why this SCD with momentum also help us in smooth updation process. That means you may get the smoother process. That means first your initial error is 0.08, and then your error may decrease to 0.07, and after 0.07 again the third fourth iteration, your error may be 0.05 and again 0.04. So it gives you a smooth process by introducing this beta term. Again, this is another considered value to increase the to give the smoothness to your gradient descent. And again, we have the other one is RMSprop. Here, um, instead of here we have the learning parameter, right? So instead of using the same learning rate everywhere, so initially you may give the learning rate as 0.1 or 0.2, but here in your RMSprop, instead of using the same learning rate everywhere, it adapts the rate for each parameter. So depends on um, how far it is from the target value. It will adjust the learning parameter. Initially, it may be 0.1, but later when it is close to the target, then we need to decrease the learning parameter. So if we are close to the target, then we may decrease our learning parameter to 0.09. Okay, so it won't be the same learning parameter for every iteration. It will change according to the situation. So it adapts the learning rate for each parameter. Finally, we have the Adam optimizer. So this is the again go-to choice for many deep learning problems. So this Adam optimizer combines both of these approaches, SGD with momentum and RMSprop. Okay. So this Adam optimizer can make you a smooth convergence and also it has the capability of dynamic learning rate. Okay, if both of this 1 and 2, SCD with momentum and RMSprop, both functionalities are contained in your Adam optimizer. That's why this is your go-to. It has all of these features, right? So it has the momentum capability, it can reduce the noise, and it has the dynamic learning rate capability. Okay, that's why it is consisting of all of the best things from this first one and second one. That's why we will use this Adam optimizer. So if you observe from the entire things, we have some go-to choices. So in case of activation functions in hidden layers, ReLU is your go-to choice. And during your output layer, so based on your problem, if it is a binary classification, then Sigmoid is your go-to choice. And if it is a multi-class classification, then softmax is your go-to choice. And again, during our loss functions, so if you have a binary classification problem, so you need to use this binary cross entropy. This is your go-to choice. And if you have multi-class classification problem, this categorical cross entropy is your go-to choice. On this MSc and MA are for regression problems. Here for optimizers, Adam optimizer is your go-to choice. You may also use this STD with momentum, RMSprop, and gradient descent, but Adam optimizer will give you the good performance because it is having the capabilities of all of the remaining optimizers. So it has capability of SCD with momentum, it has capability of RMSprop. Okay, and we'll see some best practices. So weight initialization, some regularization, dropouts. So these are very essential in our deep learning entire process that can make a difference while training your model. So let's start with the weight initialization. So this is literally like when you start your neural network training process, you are initially giving some weights, right? Some random values, right? So this Xavier and chlorate and He initialization techniques are used to assign some weights. Okay, those weights are not too smaller, not too bigger. Okay, those will be in some particular range. So this Xavier, so he's a scientist, and also he is also a scientist. So they propose different initialization techniques. Okay, and again, so this is used to um, prevent this vanishing gradient problem. So these values won't give you a very larger, and it won't be a very smaller. So it may be like point. It may be like in the range of 0 to 1. Okay, they initially our random weights will be initiated like this in this particular range 0 to 1 or so. It is very important to use these techniques because randomly you can't assign weight of 5 or weight of 10. So if you initialize some larger weight values, then you may get the higher errors. Okay, that's why you won't go for higher weights. Initially we'll start with some smaller weights. Then if you move to the regularization, so this L1 and L2 regularizations are most common techniques. So we also saw about this L1 and L2 regularization during our regression problem. So during our linear regression, these techniques generally prevent the overfitting problem. Okay, this generally prevents the overfitting problem. That means overfitting means so your model will be too specialized to a training data. That means your training data will be very good. Okay, your training accuracy. Let's say your training accuracy after training your model, your accuracy may be 98, 95. So your model works well with training data, but again it will fail with the some newer data. So whenever um, let's say like you are getting a new data, you, you may get some false output. That means if your output is 0, you may get the value as 1. Even though your training accuracy is good, your testing accuracy decreases. So this is your overfitting problem. That means your training accuracy is good, but your testing accuracy is not good. Why this is happening is because of overfitting. Your model is too specialized to your training data, but not with the new data. So this is meant by the overfitting problem. Okay, then we have the dropout. So this is one of the most effective techniques for preventing this overfitting problem. Okay, so during training, so this dropout randomly deactivates some of the neurons. Let's say, like if your hidden layer is having 64 different neurons, if you be the dropout as zero point 0.2 during your training process, 20% of 20% of your neurons get deactivated. So why we are using this dropout means, so if you use this dropout, then your neuron, so this prevents neuron from becoming too dependent on each other, and leads to more robust learning. Okay, so when you remove these neurons during your training, so this network is forced to find multiple ways to solve the same problem. That means, let's say if you are deactivating 20% of your neurons, then this network is very forced to learn multiple ways to solve the same problem. That means it leading to better generalization. That means you are not giving everything to your neuron. So you are telling your neuron to search for the multiple possible ways to solve this problem. Okay, so these three techniques works uh, work together. That means first, good weight initialization gets your network started on the right foot, and again this regularization keeps your network from becoming too complex, and this dropout ensures it learns robust and most generalized patterns. Okay, so that's why these three techniques are very important. So good weight initialization is it's a starting point, and again maintaining this regularization and ensuring your model learns the most robust and generalized patterns. That's how you will get the good accuracy during your training and testing. So this is entire working of your ANN algorithm. Okay, it starts with the input layer and it goes to the hidden layers. So in your hidden layers, your weights will get multiplied with your input and bias will be added. On top of that, activation function will be applied, and then it gives some output. Based on that output, you will calculate your loss, and then you will do the back propagation. So during your back propagation, your weights and biases get updated using the chain rule of derivatives, and then again the iteration starts once again from the starting, and again you will get a different output. So this is how you minimize your error. So let's see the practical implementation of this algorithm, how to implement everything with a code. Okay, so this is my project structure. So if you want to start this project from scratch, then it is better to create a virtual environment at first. Um, why this virtual environment means, so basically in Python projects, so imagine you're working on multiple projects, and each project requires different versions of your same libraries. That means in your code you will use different libraries, right? NumPy, pandas, TensorFlow, Matplotlib. So let's say like each project needs different version of your same library. Then if you install everything globally, then it may erase issues. That means initially your first project needs the Python version of 3.10, but your second project may needs the Python version of 3.12. Okay, that's why based on your project, you will create two different environment, and in every environment, you will give the versions of your choice of your libraries. So that's why your virtual environment comes in. Okay, so they create some isolated spaces for each project, so that you can give your libraries and dependencies whatever version you want. They don't interfere with each other. let's say like if you want to create a new virtual environment, then first I'll create a folder over here with ANN project. Then I'll open my VS Code. I'll open this folder. Okay. Now, now this is my folder structure, right? So I'll go here to terminal. So if I want to create a new environment, then I'll give the command as is conda create -p and the name of my environment. Let's say it is venv, and let's say like I want to give the Python version of 3.10, and then I'm giving this -v. Why? That means it will ask some different questions. For all those questions, the answer is yes. If I use this command, then my environment will get created. That means some isolated space to determine the versions or to determine packages. Okay. Now my environment is created. In order to activate this environment, I need to give this command conda activate. Okay. Now I'm inside my virtual environment now. Okay. Now in that space, let's say that I'm creating a new file called requirements. Okay, requirements.txt. In this file, in this file, I'll give the names of the all of the requirements, all the libraries which I needed for this project. So I mentioned here TensorFlow, Pandas, NumPy, Scikit-learn, TensorBoard, Matplotlib, Streamlit, Keras, IPyKernel. So I need all of these libraries for my project. So that's why I specified all of these names inside this file requirements.txt. And again, I need to go to the terminal, and now I need to give this command called pip install -r requirements.txt. Then it will install all of these libraries inside this file. So it will go and install each of the every library, TensorFlow, Pandas, NumPy, Scikit-learn, all of this. Okay. Now my virtual environment is created and my requirement file is created, which contains all of my required libraries. Now, first I created this file, experiments.ipynb. Okay, so this is my Jupyter notebook file. I given this extension as ipynb. So here, our first step is training our model. Okay. For training our model, in order to go to that process, first we need to import these libraries, pandas, and from sklearn model selection, I'm importing train test split. So again, from sklearn or pre-processing, I'm importing standard scalar label encoder. Okay, so these pandas is our data handling tool. So it works with data frames, tabular formats, and we have this train test split. It helps us to split our data into training and testing, and we have the standard scalar and label encoder. So these are our data pre-processing tools. So the standard scalar help us to reduce the, I mean, it changes the values in some specified range, and label encoder. So this label encoder, let's say if it changes the categorical columns into numerical. So let's say if you have a male and female, then it converts male as 0 and female as 1. And then I'm importing this pickle file. So this is like a save. We'll use this pickle to save our model. Okay. So we'll save our model in order to use it later when are required. So to save our model, I'm using this pickle. First, I'm loading the data set using read CSV. So our data set is churn modeling. So we have the columns like row number, customer ID, surname, credit score, geography, gender, age, and our target value over here is exited. So in our target column, we have ones and zeros. That means maybe churn or not churn. We need to predict this value, 1 or 0, based on this customer information. So ID, credit score, geography, gender, whether they may churn or they may not churn. So this is about our data set. And first, so let's see if you observe this data set, we have the columns like row number, customer ID, and surname. So these are unimportant in our data set. That means these columns won't help us to train our model. That means these columns won't influence our target column. Okay, that's why. So there is no particular use this with these columns, row number, customer ID, and surname. That's why I'm dropping this irrelevant columns. Okay, for that I'm using this function drop, and I'm dropping this row number, customer ID, and surname, and axis is equal to 1. That means axis equals to 1 means drop column wise. Okay, it will check the columns for this row number, customer ID, and surname, and these columns are dropped. If you observe your data set now, the first three columns got removed, and now if you see this, you have credit score, geography, gender, age, and tenure. Next, so look at this gender column. Okay, it contains male and female values, male and female. But so our neural networks can't understand this text, right? So what we need to do is we need to convert this into numbers by using label encoders. So first, I'm I'm creating a label encoder object, label encoder of. Okay, I'm taking this into a variable called label encoder gender, and now I'm using this fit transform to transform our data. First, this fit part. So this fit means it learns what categories it actually exists. So we have male and female categories, and then I'm transforming it. So it converts these text features into numbers. That means typically zeros and ones. Male will be 0 and female will be 1. Now, if you observe your data set, so you see these values like zeros and ones, right? So this female is turned into 0, and this male is turned into 1. So that so now it is in zeros and ones. So your neural network model can able to understand this. Next, we'll see the encoding method for geography column. So here, if you observe in geography, you have three different categories. So France, Spain, and Germany is the third category. Okay, we have three different categories: France, Germany, and Spain. Okay, now again we need to convert this categories into numbers. For this, we are going to use one hot encoder. Why one hot encoder and why not the label encoder means here for gender we use the label encoder, right, to convert categorical column into numbers. But here we are using one hot encoder. That is because if you use label encoder, we may get the values like for France it may be 0, for Germany it may be 1, and Spain it may be 2. So this suggests that Spain is 2 times more greater than France. But this is not a correct sensible thing. So your countries don't have any numerical order, right? So it will your model should treat all these countries as a one particular range. So if you give your Germany has 2, your France is 1, and your other one is 0, then you are showing some differentiability between these categories. So you don't want to do that. So whenever if you have categories more than 3, then try to use this one hot encoder. Okay, again I'm initializing this one hot encoder, and again I'm using this fit transform to convert this geography column. two zeros and ones. So here each country gets its own column and one appears per that column. If you observe over here, so your first row geography is France. So, so it is turned as 100. That means for France, it given the value as 1, and Spain and Germany it kept as 0. That means you are telling your model. So this is a France. In the case of Spain, it keeps the 1 over here. That means let's say like your first one, this one is France, and your second one is Germany, and third one is Spain. Okay. If it is a France, then 100. If it is a Spain, then 001. And if it is Germany, then 010. Okay. For France, 100. And for Spain, 001. And if you go for Germany, it keeps the 1 over here, 010. Okay. Next, we are using this particular function called get future names out. So let's say this is our initialized object at 1 hot encoder 0. So with this, I'm using the new function called get future names out. So when you run this command, we get the names of our new encoded columns. Okay, initially we have France, Germany, and Spain as your categories, right? So whenever I give this get future names out, it gives the name of our encoded columns. So first one is like your geography France, and second one is your encoded column geography Germany, and third one is geography of Spain. Now here, so I'm taking this encoded geography data. So I'm taking this encoded data and I'm converting into a data frame. See this pd.data frame. I have this array like values, right? I'm converting this array like values into data frames, and I'm giving the column names as these future names. Okay. If you see this array is converted to data frame, and the name of the columns are these futures. Okay. Columns equals to 1 hot encoder dot get future names out. So if you give this function, then you will get the names of your encoded columns. Okay. I'm using these names as my column names. So geography of France, Germany, and Spain. Okay. So each row will have 1 in exactly one of these columns and zeros in the others, indicating which country the customer is from. For example, your row 1 is France, then it will keeps the 1 for the France and remaining as 0. If a particular row contains the geography as Spain, then it will keeps this 1 over here and zeros in the remaining. Next, what we are doing here means, so this is where I'm bringing all the preprocessor data together. I have my geo-encoded DF separately, and also I have my input future separately, right? Input data set separately. So I'm adding both of the things. So I'm adding my geo-encoded DF and my initial data set. Let's say like, so I'm adding my data set, okay, data, and my geo-encoded DF. That means my encoded geography columns. So here I'm initially removing this geography column, okay, because we don't need it anymore, right? So we have our encoded version of this geography column, okay. That's why I no longer needed this geography column. So I'm removing this from my initial data set, data.drop, comma, I'm adding my geo-encoded DF, my encoded version of my geography column. So I'm adding both of this geography France, Germany, Spain to my data set. Okay. Data comma geo-encoded DF. Now, if you observe this output. So you have the credit score, gender, age, tenure, balance, products, haircut. Your geography column is removed over here, and then this geo-encoded DF is added at the end after exited. So your columns geography France, geography Germany, geography Spain. Both all of these three are appended to your data set. Okay. So now instead of geography, so let's say if your geography is France over here. Okay. Instead of this column, we got three different columns. Okay. Whenever the row is France, then it will give the one over here remaining as zeros. This is what we did now. So we separately we calculated the numerical columns, numerical values for this geography, and we appended it to our data set. Next, I'm saving these models. Okay. Um, if you see this, I'm opening the new file in the write byte mode. I'm specifying the name as label encoder gender.pkl as my file name, and this label encoder for gender. If you see this, so I have done some transformation for gender, right? Initially, so this gender transforms male and females into zeros and ones, right? So I'm taking that functionality and I'm saving this as a some particular file. Okay, this is my object label encoder gender, and I'm saving this object functionality inside this file label encoder gender.pkl. Okay, and again in the same way, I'm taking my one hot encoder object and I am saving this as a pkl file. That means pkl file. Once again, why I am saving this means because I need to use it in the future. So whenever I get the new test data, I need to use the same functionality and convert those test data into, again, for the test data also you may have the gender column and geography column, right? So I need to use the same functionality and convert those into numerical values. Okay. So I'm saving these models so that I can use it later. So whenever if you execute this code, then you will see two new files created. One with label encoder gender.pkl, another with one hot encoder geo.pkl. Two different files. Now we are dividing a data set into independent and dependent features. So this is where we separate our data. So until here, we read our data set, we transformed the categorical features into numerical features, and we saved those label encoder and geo encoder as different files. Now I'm dividing my data set into X and Y. So for X, so I'm taking all columns except this exited. Okay, data dot drop off exited. Apart from this column, I'm taking all the remaining columns in the X. And Y is a target variable, right? So exited is a target variable. So this is what we're trying to predict, Y variable. Okay. Next, we are splitting the data into training and testing. For this, I'm using train test split. So with train test split of X comma Y, X data and Y data, and test size is 0.2. That means 20% of the data for testing and 80% of the data is for training. And random state is some 40 to some random value. So we'll get the every split, same split every time. Now I'm using standard scalar. So this standard scalar, use it to standardize your numerical features in the same scale. Okay. So I want to normalize those values so that our model don't show any of the bias on those columns. It should treat all the columns in the same fashion. That's why I'm transforming all of my numerical features into the same scale by using standard scalar. Then I'm fitting and transforming my extrain data to my standard scalar. And also I'm transforming my X test data to the standard scalar. So this fit transform on X train, basically it learns the scaling parameters and applies them. And for transform, it applies the same scaling technique used in this X train. Okay. So we are transforming our futures to the same range now. If you see this, all of these numerical futures are converting into some specific range 0.3591 minus 0.65. And again, now I'm saving my scaling functionality as a folder, as a new file once again. I'm again taking the name as scalar.pkl and I'm taking the scalar object and again I'm saving this as a new file. Okay. Now I created three different files. One is label encoder for gender, one hot encoder for geography, and the scaling functionalities, scaling file. So whenever I get my new test data, I'll use all of these three functions to transform my data accordingly. So now this is your whole your data set now. So we divided into training and test bed, right? So after dividing, we need to train our neural network, right? So this is the main important now, ANN implementation. Okay, first, you are importing some specific libraries. You're importing TensorFlow, and from TensorFlow.keras.model, we are importing the sequential. So this sequential is like it is from Keras. So it allows us to build our neural network layer by layer. So we have our input layer, hidden layer, and output layer, right? So this sequential help us to build our neural network. Okay. And again, from TensorFlow.keras.layers, we are importing dense. So this helps us to create our fully connected neural network. So here each neuron inner layer is a dense layer, okay? Is connected to every different neuron, right? So the in hidden layers, every neuron is connected to other neurons in the other hidden layer, right? So this denses help us to create that functionality. That means it will help you to connect two different neurons. And from callbacks, so from TensorFlow.keras.callbacks, I'm importing early stopping on tensor board. So these callbacks basically this early stopping help you to prevent the overfitting problem. So it will stop the training whenever the model stops improving. Let's say like if your model is you given 100 epochs, let's say you are telling your model to train your entire deep learning model for 100 times. Let's say until the 10th iteration, your weights are getting changed. So your loss function is decreasing. And again, from 11th iteration, your loss is not changing. And again you are getting the same value from the 11th iteration. So it is no use, right? So again, calculating 100 different iterations, if your weight is not updating, then you are losing your computational time, right? So that's why I'm using this early stopping. So um, it's whenever the model stops improving, then it automatically detects and stop your training process. And next we have this tensor board. This is a visualization tool which help us you to monitor your training process. Okay, it will track all the losses. What is your loss what is your validation loss, what is your accuracy. Okay, this help us to track all of your training process. And now I'm also taking this datetime. This is useful to create timestamps for your TensorBoard logs. So I'll tell about this logs and datetime. First, now after importing this, I need to build my ANN model, right? So for that, I need to use the sequential. The sequential help us to create the create the deep neural network layer by layer. First, first I'm implementing my first hidden layer, okay, with the help of dense. Okay. So in my first hidden layer, okay, okay, I'm giving 64 is my neurons. So in this layer, go and implement 64 neurons. Okay, I'm initializing 64 neurons. So in each and every layer, there are multiple neurons, right? So here I'm giving 64. And again, Activation function I'm specifying here is ReLU to calculate your activation score. That means your weights are multiplied with inputs and bias will be added. On top of it, activation function will get upgraded. So for your hidden layers, I'm specifying this ReLU activation function. So this ReLU activation function gives the values as if it is a positive value, positive input, then the same output. If it is a negative value, then it turns into 0. So ReLU is my activation function, and I'm determining my input shape. It specifies how many futures we are inputting. So we need to specify our input layer, right? So for that, I'm giving how many columns I'm actually having. So those are my input futures, right? So extra in dot shape of one. That means I'll get my column value. Let's say here I have 13 columns. So 13 is my input shape. That means 13 input futures. I'm giving it to the first hidden layer. Next, I'm creating the another hidden layer. Now, my second hidden layer contains 32 neurons, and the activation function I'm using is the ReLU, the same one. And now here for the second hidden layer, I'm not specifying my input layer because we already specified that in the during our first layer, right? So here no need to again use the input shape. Okay, it generally we will use this input shape for our first hidden layer only. It automatically this hidden layer 2 takes from this first one, first hidden layer. Now, this is a third output layer. So it is our binary classification problem, right? Zeros and ones. So my output layer contains one neuron. Okay. Because we are doing binary classification problem, and our output values will be 0 or 1, anything. So here I'm using sigmoid as my activation function. Okay. So I need the values between zeros and ones, right? So that's why I'm using this activation function called sigmoid. So for hidden layers, my activation function is ReLU. And for my output layer, my activation function is sigmoid. So now I'm printing the summary. Okay. Now I designed my entire deep neural network structure. So now I'm taking a summary of my structure. So this summary, it will give you a detailed overview of your neural network architecture. Let's say like it will analyze how many weights are there, how many biases are there, so how many weights are connected to how many neurons, and again those neurons generating how many weights, and again how many biases in the neural network. So it will calculate all the weights and biases. So for your dense layer, for your first hidden layer, so you have 832 parameters. That means 832 different weights and biases. And for second layer, so you are having like 2080 parameters. So we need to, during the backward propagation, you need to update all of these parameters. That means it consists of all different weights and biases. Okay. So total how many are there? And total params. Okay. For hidden layer 1, 832, hidden layer 2, 2080, and for output layer 33. So overall, combinedly, we have 2945 different parameters. That means those many weights and biases in your entire deep learning structure. Now, I'm importing my TensorFlow, and from TensorFlow.Keras, I have this function, this called optimizers, and I'm taking Adam as my optimizer. So why this optimizer? It helps us to update its weight. Okay, I'm taking the Adam optimizer. So already saw about different optimizers, like gradient descent, SDD with momentum, RMSprop, and Adam. So Adam contains the functionality of SDD with momentum and RMSprop. So this is my go-to choice. So I'm taking my Adam optimizer, and my learning rate is 0.01. So this Adam actually combines the benefits of adaptive learning rate and momentum for faster convergence. Now I'm taking my loss function from TensorFlow.Keras, and from losses I'm taking binary cross entropy. So this is a binary classification problem. So our go-to choice is binary cross entropy. So this is perfect for binary classification problem. So it measures how far our predictions are from our actual values. Okay. So here is my optimizer and here is my loss function. Now the thing is your deep neural network is ready here, and you also initialize your optimizer and loss function, and finally you need to compile this model. For compiling, you need to use this dot compile, model dot compile. So my entire model is stored in this variable model. So model dot compile of, here I'm specifying my optimizer. So my optimizer is OPT. So here OPT contains my optimizer, Adam optimizer. Okay. And my loss function is binary cross entropy. You may give the it you may give binary cross entropy like this, or you can initialize this loss as your loss. Okay. Anything is fine. And metrics, I'm also taking some metrics, which means here accuracy. So it tells Keras so what additional measurements to track during your training. So accuracy is generally it is the percentage of correct predictions. Okay, I'm taking the optimizer, loss function, and metrics, and I'm combining my model. Next step is, so initially here we took different callbacks, right? Early stopping and where is this? Yeah. Early stopping and TensorBoard. So from callbacks, we imported this early stopping and TensorBoard. So let's see like what's the use of this early stopping and TensorBoard. First, first I'm implementing my TensorBoard strategy. So this is a basically visualization tool help you to monitor your training process. Okay. First, I'm specifying some directory. So it creates a unique directory. So which tracks all your training logs. Okay. So I'm specifying my structure as my folder structure as logs underscore logs fit. That means go and create a folder called logs, and inside this logs, go and create a folder called fit, and inside this folder fit, create every training log in this format. Datetime.datetime.now. That means from datetime, take the current date and time and change that current time in this format: year, month, date, hour, minute, second. Okay. Every time when you train your model, the training logs, the training details will be stored in this directory. Okay. After, I'm going to use this tensor board, and I'm giving my log directory to this tensor board. I'm giving the histogram frequency equals to 1. That means it will log all the data into your histogram. So whenever if you see this visualization tool tensor board, it will show you some graphs basically, so some visualization graphs. In those graphs you will notice training losses. So what is the training, what is your error for your first iteration, what's the error over the second iteration, and what is the accuracy during your first iteration, what's the accuracy during a second iteration. It will show everything in a visualization format. Okay. And now, so I set up my tensor board callback. Now I'm setting my early stopping. So this early stopping callback actually prevents your overfitting. It monitors the validation loss for your model improvements. And if loss doesn't improve for some specific epochs means how many times your model is training or your data. Okay. If your loss doesn't improve over the iterations, some specific iteration, then your training stops. Okay. So I'm monitoring my validity loss, and patience equals to 10 over here. That means it will check for 10 different epochs, 10 different iterations of your training. So if there is no improvement over 10 epochs, then your training stops automatically. Then here I'm restoring my best weight equals to truth. It ensures you keep the best model version. That means if it stops over the 20th iteration, and if your model, if your ANN model considers that is the best training score you got, best accuracy and the least loss you got, so then it will restore those weights and biases values. Now I'm training my model over here. So for that, so now I have implemented my structure, deep learning structure using sequential, and then I initialized my ADAM optimizer, loss functions, so everything. So whatever I need for my deep learning model, I implemented everything. So first, I given my inputs, I created my dense hidden layers, and I given my loss function, and I given my optimizers. So everything whatever I required, I implemented. I also took this additional things, early stopbacks and TensorFlow. Now the thing is, I need to fit this model now. So if you use this function model.fit, then your actual training process will start. So inside this fit, I'm giving my data. So my data here is X train, Y train. So this is my input data, and I'm giving my validation data. Okay. Go and validate on this data, X test, Y test. So this is my testing data, training data, testing data. And I'm giving epochs equals to 100. That means it will train for a maximum of 100 rounds. That means 100 different times. So 100 different times, the weights will get update and the bias will get updates, and every time for 100 iterations, so you will get different loss values. Okay. So I'm giving this 100 rounds. Now I'm taking the another one, like another parameter called callbacks. So here in this callbacks, I'm specifying the both of this TensorFlow callback and early stopping callback, both of my variables, this TensorFlow callback and this early stopping callback. So here is my training data and my testing data and my callbacks, and go and do this training process for 100 times. Okay. Now my training process will start. If you observe here, epochs 1 by 100, 2 by 100, 3 by 100. So every round, so in every round, your entire data will get trained. So if you see this, there are 250 rows. So all this 250 rows is trained during your first epoch. And if you observe, your accuracy is 0.81 and your loss is 0.43, and your validity, accuracy, validity, loss. And again, second epoch, again your model get trained. If you see this, your accuracy is improved over here during your second epoch. First 81, 0.81, second 0.85, and again third 85, fourth 86, 85, 85, 86, 86, 86, 87. If you observe over here, I given the patient value equals to 10. That means if there is no particular improvement over 10 different epochs, then my model got automatically stops. Here, if you see this, I given my epochs as 100, but my model is trained only for 24 rounds. After 24 rounds, my model stopped my training. Why? Because I specified the patience equals to 10 for 10 different rounds. So there is no particular improvement in my accuracy. If you observe this from over here, mm, if you see this, here you have 80 for the 12th one. If you have here 80, 0.86, and again 13th round 0.86, 14th round 0.87, 87, 87, 87, 87, 87. So if you observe this 86, 87, so there is no particular improvement over here. It is just revolving around 0.87 only, right? That's why your model stopped training after this particular iteration. Okay. Now your model gets trained, and I am saving my entire model now. Okay. Model.save off. I'm saving this with H5 extension. So now we saved our trained model in H5 format. So this is cool, right? First, we taken the data and we converted categorical into numerical features, and we splitted our data into X and Y. After splitting, you used the sequential to build your ANN model, and then you initialized all your optimizers, loss functions, and you implemented this callbacks, and then you fitted your model using your training data, testing data, and your callbacks. So now my model got trained. Now after training, what we need to do? We need to predict the things, right? So if you observe the accuracy, now your accuracy is 0.87. So 87% is your accuracy. So now with this trained model, I need to predict for my new data. For that, let me show you this code. First, again, I'm importing these statements, TensorFlow, Pickle, Pandas, NumPy. Okay. From TensorFlow.keras.models, I'm importing load model. Why this load model is? So previously during our training, so we saved our files, right? So one hot encoder, label encoder, scalar function. Now for my prediction, I'm loading those encoded files. Okay, I'm loading those label encoder and the geo encoder so that I can use those functionalities for my testing data now. Okay. Again, instead of this is the backend process actually. So whenever if you create some web application, so user will go and enter some values, right? Let's say like their credit score is 750 and they're having credit card and their total amount is something 60,000 everything. So during a training process, we converted those values into numerical format, and also we changed the scales, right? So all the numerical format using that scalar, so we standardize out the values, right? So again for testing also we need to do the same process. So whatever the new data may be, those data need to go into those functions. Let's say like if it is a gender, then if the user specifies male, then that male needs to go inside this function, and again it needs to transform into 0 or 1. And if the user specifies their location as Spain, then that Spain need to go to this geo encoder, and it needs to transform into 0111 or 100, anything based on the value. Okay. And the remaining numerical features need to be scaled using the scalar file. Okay. I'm again using the saved models for my prediction data set. So I'm loading my models using pickle.load. Okay. I'm specifying my name, and now I'm using this read byte mode. Okay. Go and uh, fetch the data from this file. Okay. And save that into this variable label encoder 0. And again, label encoder gender. Go and fetch that file and load that file into this variable. Okay. And again, scalar.pickle file. Load and save into this function scalar variable. Okay. Now I want to predict for the new input data. Let's say like my new input data is this one, credit score 600, geography France. Let's say user given this input data 600 France, gender, age, tenure. So these are my columns in my data set. Okay. Now this is my new input data. Now with this input data, okay. So now I'm using these functions over here. So first I'm taking this geography France. Okay. I'm I'm pushing this France into this function, geography function, label encoder geo. If you see this, label encoder geo dot transform. So I already used the fit transform method, right? Initially during in my training process. So now I'm just using this transform function to convert this geography into one hot encoder vector. Okay. So my input data of geography, I'm taking this and I'm transforming this geography by using this function encoder geo. Okay. Now after transforming, I'll get an array shaped. So I given here as two array. So let's say this is geography is France, right? I may get the vector of 100. So This 100, I'm creating a new data frame over here. Okay. So pd.data frame of geo-encoded this 100 data, and I'm giving the column names as again label encoder geo dot get future names out of geography. The get future names out gives me the encoded column names. What are my encoded column names? Geography, France, Germany, and Spain. Okay. So this is my new data frame now for this value for France. Now I'm converting this input data into new data frame. Okay. So this is my input data frame. Now the next thing remained over here is I need to transform this gender as well. Let's say like the gender here specified as male, right? So this male need to be pushed into this function, label encoder gender. Okay. This label encoder gender. So in my entire input df, I'm taking this particular column gender and I'm transforming that gender. So from input df, I'm taking this gender. So input df of gender. So I'm transforming using this label encoder gender. If you observe the output now, gender is now converted to 1. Okay. So that means 1 means here it is male. So your male is converted into 1 over here. Now we have our geo encoded df geography, France, Germany, Spain. As similarly in our during our training process, we merged both of these data frames, right? Here again, I'm doing the same thing. So I'm using this concat and input.df of input.df dot drop of Germany. So in this entire df, I don't want geography column because I have this encoded df, right? I need this. Okay. So I'm combining both the data frames, my input df and my geo encoded df. So now this is your entire df, entire data frame. So here your categorical variables, gender and another one is geography is converted into numerical features, right? But here your credit score, balance, estimated salary is having some numerical features. So during our training process, we scaled all of these numerical features in particular range, right? So that's why again for testing also I need to do the same. Again, I'm taking the scalar function which I loaded before, the scalar, and I'm transforming my entire input df, this entire df, so that again it will transform all the values in some particular range over here. Okay. Now I turned my categorical features into numerical, and I transformed my numerical features into some particular range. Now my input scalar data is ready over here. Okay. Now I need to predict on this data. Okay. On this array data. So I'm using model.predict of input scaled. Okay. I'm giving this entire array, take this entire array and predict using my trained model. So here I'm getting some value. I'm getting the value as 0.0264. Okay. I'm getting some particular value over here. So this is basically stored in a 2D array. So I'm taking this value itself in a new variable prediction proba. It's my prediction probability. So this value is stored in the prediction. So prediction of 0, 0. That means this is a 2D array. I'm taking this value 0.02. If you observe this, my prediction probability now is 0.0264. Okay. Now I'm giving the condition over here. If my prediction probability greater than 0.5. Okay. So in your output layer, you take this Sigmoid activation function, right? So it gives the values between zeros and ones. So here it given the value 0.02, which is between 0 to 1. So generally for Sigmoid activation function, we'll take the threshold as 0.5. Okay. If your prediction probability is greater than 0.5, then the customer is likely to churn. That means if it is greater than 0.5, then turn the value into 1. Okay, then your exited value is 1. That means customer is likely to churn. If it is below 0.5, the customer is not likely to churn. So here 0.02 is below your 0.5, then your else statement will execute. So the customer is not likely to churn. Here your output value is 0 over here. Okay. So for this particular input data, your customer is not likely to churn. Okay.
That
He's
that means what?
my
Not
churn
likely to
means,
yeah.
yeah. Here
Yeah.
churn in the sense it depends on problem statement. Let's say like here it is a credit. You are having this column credit score, gender, age, tenure, balance. So this is some bank information, right?
Correct.
Balance, credit score, gender, age. So this is your bank information, right? Let's say like your bank is going to launch some new product. Okay.
Okay.
So based on this customer information, let's say like this particular customer, so his credit score is 600 and
Okay.
his bank balance is 60,000 and he already owned two products and he's also having credit card. Okay, and he is very active member. So with these details, I'm determining whether my customer is going to buy the product or not. Okay, if the customer is not likely to churn means, so there is a probability of customer may buy my product again. If the customer is likely to churn means, my customer probably won't going to buy my product. Because here for example, if your customer is having lower credit score, lower bank balance, and he's not having credit card and he's not an active member, then you may get the output value as close to 1. That means your customer is likely to churn. That means he's leaving. That means he's no longer he's going to buy your product. Okay.
Okay. Okay.
So this is churn. Okay. Churn means leaving the things. He's not going to he's not going to buy that product. So here with this input data, the customer may buy your new product, which is going to launch. It depends on the problem statement. Okay. So now this is my probability, point 0.02, and the customer is not likely to churn. So this is my prediction. So I trained my model and with the new input data, I predicted my outcome. Here with these predictions, then the bank may decide, okay, how many customers are going to buy my things, how many customers are not going to buy my things. So they will have some clear estimation about this. Okay. So overall, so we started by understanding what is deep neural networks, so what is deep learning, and also we saw about artificial neural network. So in this artificial neural network, we have input layers, hidden layers, output layers, and we have activation functions, loss functions. After that, we saw practical implementation of ANN. So first we started with the training phase. We did some data pre-processing thing, and next we build our model and we saved our trained models and preprocessors, and then we are predicting on the new data, so by loading the trained models. So by loading these trained models and again using these preprocessors, I'm transforming my data and predicting on that data. So finally I'm making my reliable predictions based on my trained model. Okay.
Yeah,
So this is
I have another question actually. So right
Mhm.
now we have implemented code using TensorFlow, correct? Using the
Right.
deep learning model. So
Yeah.
we have seen that there are algorithms like regression model and there are like a classification. There might be some other algorithms are there, right? Why we need to go with the deep learning, the tensor models basically? What is the difference between the other algorithms and this one? Is there any reason?
Okay.
Just
Yeah, there is reason.
just cut
Yeah,
it
there
out.
is
Yeah.
particular reason. Yes, yes. So here we implemented with the ANN, right? So,
Hmm.
so your ANN model has the capability of understanding more complex patterns in your data. So for this particular data set, you may go for supervised algorithms. So you may use the logistic regression, support vector mission. So you will get some output, right? The same ANN also works for the classification problem only, classification and regression problems. But what's the main difference over here is for those supervised learning than your supervised learning models, this ANN may understand your complex patterns and it may give you more accuracy than those algorithms. Okay.
Okay. Mhm.
And other thing is, for example, your entire machine learning deals with your supervisor machine learning deals with some structured data, right? So you are having some structured data, so tables and columns, and you will have some labels, zeros or ones, or for if it in the case of regression problem, you will have some value, right?
Right.
But what if your data is containing some text, okay? Or what if your data is containing some images? So for those kind of things, we are not going to use the machine learning, right? So for text-based problems, we may go for natural language processing, and for image-based problems, we need to go for convolutional neural network. So which is again in the deep learning, and again you have the concept of RNN. So RNN basically deals with this text-based data. Okay. So this
Okay.
ANN deals with the classification and regression-based data, so structured data, and your CNN deals with the image-based data, and your RNN will deals with the text-based data. Okay. So
Okay.
this CNN and RNN will learn in the next classes. So for today, we learn about ANN,
Right.
basically for the classification and regression problem.
Right. Thank you.
Thank you for watching. Please like, share and subscribe to KKR Gen AI Innovations channel.